and welcome back to our series of training on the basic cybersecurity concept on Linux. We have started to have a complete or reasonably complete overview of the general mechanism which are available on Linux to protect your machines, and what you should do to try to minimize the risk of being hacked either directly or indirectly by malicious code, and in the case that your system has been penetrated, to limit the capability of the malicious code to progress into your own system. So this is the last lesson, and we're going to talk about virtual machines and container. I will be very honest with you. You still have to work as well, understanding what level of security you should put on your network, which is another part of capability which are available for malicious people and malicious code to progress inside a company. And this is not part of that code, that course. Neither is the specific vulnerabilities which can be activated through Windows machines and Windows servers, in particular through the use of Active Directory, which is a very powerful tool, but which can be also used by malicious users in a very efficient way to penetrate system. So we'll not go there, but that's just to give you some idea what you may want to do after this course. So in this lesson 6 we are going to talk about the general concept of virtual machines and containers. Then we will look at Docker specifics, because Docker is pretty popular. And we'll conclude by a quick look at the limitations which are inherited by the use of such technologies. So people who want to run virtual machines and container in general are trying to run isolated services independently of their physical instantiations. And originally that was not done for cybersecurity at all. It was mostly done to allow to not have to manage multiple versions of different, mostly Windows machines, and keeping compatibility with application while the hardware was evolving. And then it started to be used to consolidate servers. It's been used for a lot of things. But cybersecurity was not the initial driver when that type of technology was created. It was more scalability and long-term maintenance, and that has actually some side effect that will come later. First of all, a lot of people believe that virtualization is very new. That's actually not true at all. It's actually pretty old. It started by IBM in the 60s, and I've just put a photo of a car that was very popular in the 60s. That's a 404 from Peugeot, and my parents had one, but it was an estate version. It was supposed to be a very reliable car which could actually do easily up to 100,000 kilometers without having major problem on the engine. By the time that was a lot of kilometers. Nowadays would be pretty low kilometers, but it just gives an idea about how old the technology. Most of people realize better by looking at fashion or listening at music or looking at car what a period is. And so in the 60s it was first established in a lab on a machine called CP40, and this was driven by the fact that IBM had lost a huge contract in the MIT where they wanted to have time sharing, which was a way to share a machine between multiple users, and IBM didn't believe in the technology of time sharing. They saw that there was no use of that, and batch processing was what would ever be used in computing. And in reaction, they started to realize that potentially they may have to provide capability to run multiple machines on another one, on a single hardware, and they came out with the concept of virtualization. It took quite a bit of time to get really stable. The first really stable release is accounting under the commercial launch of CP/CMS in 1972. But still, it's quite old, and likely numbers of students in today's university were not even born when that type of technology was actually used in quite mass volume, I have to say. That was for virtualization of the operating system. You have another type of virtualization which is very popular, which has been made very popular by Java, and that started in 1995. There were a few technologies before that were using virtual machines to run applications. And obviously the concepts are very different between running a virtual machine to run an application and running a virtual machine to run an operating system. But at the end of the day, it provides at a high level a similar capability, which is to isolate an application or an operating system from the underlying hardware, allowing to run especially old code on new hardware, which was a huge demand. From a mass adoption point of view, really operating system virtualization, or virtual machines, they're called, was made popular by VMware, which actually was launched in 1988. So it's definitely more recent, but that was running on PCs, and PC before that time were not really that powerful anyhow. The container are significantly more recent. Not that the technology of container is that new, because it's based on namespaces, but Docker, which really made them very, very popular because of the adoption in the cloud starting in 2013. Now, why is that important? It's important because before the year 2000, we were not really talking about cybersecurity at all in computing and in networking. It just was not a concern. The pressure from cybersecurity started pretty recently, I would say after 2010. And even now in 2017, there are still people who believe that this is a minor problem just for the banks, and it's not for really a single small company, which is completely wrong, obviously, and we know that. But so, because it was not a big pressure, it also has not been embedded in the concept immediately, and some assumptions which were done later were actually pretty incorrect. So let's look at what is virtualization. So we've said virtualization is to run, at least on the OS virtualization, several operating systems in the same hardware. So you want to share the CPU, you want to allocate RAM areas, which are then not going to be shared as such, but probably each virtual machine is going to have area of RAM that will be reserved. And same, we're going to either allocate or share the input-output. So, for example, if you want your virtual machines to be able to talk on the network, they're going to have somehow to share the Ethernet interface. While on the opposite side, you may accept that one specific serial port is dedicated to a virtual machine. That's why I say it could be allocated or shared. In traditional server world, I would say that sharing tends to be the norm, in the sense that the CPU is going to be shared, the file system and the disk I/O space is mostly going to be shared, and same for network interfaces. The RAM on the other side most of the time tend to be allocated, even if it's not allocated statically, at least the amount of RAM you're going to be able to use tend to be allocated. What are the enabling technology? On the CPU first, the interruption. The interruption allows to decide when an event comes externally on the hardware, what piece of code is going to use it. And so you have the capability to decide that you want to allocate, for example, serial port 1, which has its known interruption, to a specific area, and interruption 2 for serial port number 2 to another part of the RAM, and then you're going to execute different codes. So that's very basic. And fundamentally, that was enabling to time share. The real big improvement that came from IBM, and that's why they actually could implement that technology, was a concept of a memory management unit, which was really a memory protection unit, in the sense that we created a virtual addresses, and this time the code was not executed anymore assuming a physical address, but assuming a virtual address which was translated at runtime into an actual physical address. That was a big change on the way to use a RAM. And that did allow to really start to make significantly more complex code and more dynamic code. Before that, the code was actually loaded at a fixed address, and mostly had to run at that address because you had some jumps that were done statically at fixed address, and you could not relocate the code. Then we started to make jump which were relocated compared to a fixed zone, but it also had the side effect that it was not always that easy to get all the RAM used. The MMU really allowed to dynamically relocate code and even to split the same program in different bits of RAM which were not even continuous. That was a revolution. The second thing that it did allow was to create an interruption when code was executed that was touching a RAM that it should not have been decided to execute. The obvious reason initially was protection. So if code was starting to touch an area which was, for example, the operating system, while it was an application code, we could dump it and say, you're trying to touch a zone of memory you're not allowed to touch. But it did also allow to use interruption not only to kill code that was doing what it should not do, but to implement virtualization, because that did allow to get an interruption where a bit of code was trying to touch a RAM it should not touch. And instead of killing the code, we're saying, okay, why it was trying to be there. And then we could find that, that's a virtual machine. And that virtual machine is trying to do an action that is actually not allowed for a virtual machine. And we're going to trap that request, and we are going to execute it by the guest OS. And so we're going to subcontract the work to the guest OS, which was a way to share things. So really the MMU was a revolutionary technology which did allow that. Since then we had new evolutions, especially sophisticated hardware today are capable to create at hardware level virtualization of I/O, operating in input-output, creating some virtual devices. So the code thinks that it's seeing a dedicated hardware, but actually does not do it. We could do as well the CPU, and we could allocate core preferences. We could, remap things dynamically, and we could create virtual device enabled by hardware. And in that case, we don't have to interrupt the code from the virtual machine and execute, subcontract the work to the host, but directly the hardware is taking care of that. So the virtual machine has really the feeling that it's working on hardware which is dedicated, but actually that hardware is actually shared, which allowed to implement it in a significantly quicker way. From a pure cybersecurity, it doesn't really change very much. At the end of the day, it's pretty similar technology. We are still sharing hardware by a different operating system which have no capability to see each other, completely isolated by hardware. But we still have underlying technology, as you can see in this small graphic with the right VMware. We have a hypervisor, and that hypervisor is still the one which has a complete access to all the resources, and so which can do things that could be pretty nasty. So from a cybersecurity point of view, what you don't want is to open capability from a guest operating system, to take the vocabulary of virtual machines, to actually attack the host
of the virtual machine, the hypervisor, which normally is running in ring 0 and has huge privileges on the capability to really do what it wants with the hardware. Now we have different type of virtualization, so and we have different model and different types. So it's just vocabulary, but people try to make a big fuss about the different model. To be honest, from a cybersecurity point of view, it doesn't really change very much. But let's look at the different model. We can have application virtualization. As I've said, an application running in Java is executed by a virtual machine from Java, so it has a level of isolation, and this is application virtualization. The same for Python. It's running on a virtual machines, which is a Python virtual machine or JavaScript. It provides a certain level of isolations in the sense that the application does not have direct access to the operating system anymore. It has to go through its own virtual machine, which can provide some level of security. It also have some side effect, which is in particular when it is a language which is compiled on the fly, like Python or JavaScript. People say interpreted, but most of the time nowadays it's more a compilation on the fly, which is done. You have the capability to download code dynamically and to execute it, same for PHP, and that can be very dangerous, because then malicious code has the capability to download extra capability after the initial infection, making the detection significantly more difficult, and also the vector of infection can be in that case extremely small. This is not the case when the code is compiled, like for example in Java, where it's still run by a virtual machine, but it's a compiled code. You have desktop virtualization, which is in that case the entire desktop and the application is running on a server, and the machine that the user is having in front of it is just doing a display. It's almost like having a long tube that would give you a visibility into a virtual desktop, which is actually hosted somewhere where you don't have access. A well-known system for that is Citrix in the professional world, and in the free world is VNC, which allows you to create virtual desktops, and they are executed remotely and in isolation from each other. Once again, those virtual desktops can be implemented with different technology, and the level of isolation between all of these desktops can be stronger or weaker depending on what you have selected. In any case, most of the times they're pretty far, and so you have to really trust the technology you're using, because direct visibility is pretty low. We have hardware virtualization. We talked a little bit about it because it's very hot, and this is the VTD, for example, enabling on Intel hardware, which is pretty popular on desktop and server, so where really the hardware provides capability to present virtual machines. You can virtualize your network, and virtualized network is a very hot topic these days. It allows to not only reduce the cost of creating complex network, but it allows to make them very dynamic, which is important when you start to do cloud computing. Obviously, disadvantages of any of those is complexity, and storage in one way is very similar to network virtualizations, where you believe you have storage, but you don't really know where it is, and it can be most of the time executed in the cloud. There is another word you will hear a lot around network and storage, and especially container used a lot as a technology putting all of that together, which is OpenStack. OpenStack fundamentally is a technology developed on a different model and type of virtualizations. And finally, you have the type. So the type, people call about type 1, type 2. I just would try to simplify it. You have power virtualization and full virtualization. To be honest, from a security point of view, there is no real difference. Power virtualizations what you do is that you modify the guest operating system in such a way that you're not relying on the execution to be interrupted by the guest trying to do an invalid operation and being rebooted to have that operation subcontracted by the host, but you modify actually the guest in such a way that it doesn't do the wrong thing and directly does the subcontracting to the host operating system. And for a long time, for example, Xen was working in para virtualizations. Now with enabling of hardware virtualizations, the difference between para virtualization and full virtualization became very, very small. And full virtualization, as I've said, is probably you don't modify the guest, and the requests are trapped by the hardware and subcontracted to the host OS. But with hardware virtualization, that difference becomes significantly smaller. So as we can see on this graphic, before the virtualizations, you had a CPU, you had one bank of memory, a few I/O, and a hardware drive. When you put the virtualization layer, you actually create virtual CPU, virtual RAM, and then that you're going to run a full operating system, which is in the modern world, when you're running with VMware or with VirtualBox or with KVM or Xen, is not going to be even modified on modern hardware, because as I've said, the difference between para virtualization and full virtualization, while people still talk a lot about it, in reality has very different. So from a security point of view, what you really have to remember is that the weaknesses in your guest operating system are going to remain as if they were running on a real hardware. There is no difference. So you still have to do your update and your upgrade, and it's not going to be done for you, and if you have a weakness there, it will stay. The isolation between the two operating systems running on the same host is extremely good. Now, you may have some zero-day attack which allows to move things, but in a nutshell, it's extremely good. Now, they are connected on the same network. That one point that needs to be realized is that this guest operating system most of the time are running on a virtual network inside the host OS, and that it's most of the time a Linux bridge. And so that means they are on a very, very fast pipe. So any weaknesses or any malicious code which is capable to propagate through the network will propagate very quickly if you have not set up rightly your firewalling strategy. So you are very similar of being independent machine connected on a very fast internal network. Your host operating system is normally reasonably well protected. It's not easy, beside of known weaknesses of your host that you have not patched by a security patch, or is a zero-day attack, and so there is no patch because you don't even know that weakness is arrived. That one is always potentially been attacked, and then it has the capability to modify directly any guest operating system because it has actually full access to them. But as I've said, it's pretty good technology, and especially if you keep your patches up to date and you work with supported software, you should be reasonably good on that level. So, benefit, side effect. The benefit are obvious. There's very strong isolation by hardware on modern hardware. So mostly for people using that, it will be x86 hardware running on server or desktop, and yeah, that is really good. But it has some side effects which are interesting as well when it comes to cybersecurity, not so much on the domain of protection, but in the domain of recovery. The first one is that you can do snapshot. Most of the host operating system hypervisor, VMware, VirtualBox or Xen or KVM, to take the most popular one, would allow you to do a snapshot. So a snapshot is really a photo of your operating system and the application taken instantly, and you have the capability to store them.
which means that if you are attacked, you can recover very easily to that known good point. Now, that known good point may still have the malicious code in, but still at a dormant level. But at least it gives you a chance to go back. You can also do replication with that model. So you can have very easily systems which are ready to start further, and they can also have the snapshot system active, so you can come back. So in case of an attack, one of the big advantages of system running on virtual machine is that if you are well organized, you likely have a second site in another place which has everything ready to run very quickly, with the capability to roll back to known good situations almost instantly. It's very, very quick. But remember that rollback through snapshot is not the perfect model, in the sense that you may still have the malicious code present, and so you have to be ready to do a check on that point, and a very detailed check to find out how you were infected, so you don't carry the same infections to come back. But for example, if you forgot to do an update and you have been attacked, you can roll back, and that's interesting. You can also roll back your volumes of data, which means that if, for example, you had a crypto locker which came and locked your hard drive, you can come back to your previous status before getting encrypted. Obviously, it will take you space on hard drive, and will cost you a bit of money in storage. What are the side effects? The number one side effect is a large increase in the OSs to maintain. Because very quickly, virtual machine being very practical, they tend to proliferate a little bit out of control. And so you, instead of having, in your domain, maybe 20 servers to maintain, you're going to get to something like 200 or even 2,000. And they still have to be upgraded for security patches, all of them. That's a very important point to realize. So in general, from a cybersecurity point of view, if you start to use virtual machines, the system is going to scale up extremely quickly, which means that you're going to have to implement technology to deploy your especially security update, and to monitor your logs, and to check that everything is right. Like if you were in a company that was at least one order of magnitude bigger than what you actually are in. So that one side effect that you need to remember. It's also a great way to keep out, or to keep in, depending how you just don't look at it, support, which are OS which are out of support. So I have seen virtual machine running code with Windows 3.14 because one specific accounting application was only running on Windows 3.14. Yes, that's practical. Yes, that is really why virtual machines were initially created, which was for a scalability issue. So you have your new machines came in, didn't run the old operating system, but you could run your old operating system as part of virtual machine. The problem is that you have no maintenance, you have no service, and you have no security patches. So that machine is extremely, extremely weak and extremely dangerous. So it may happen that you have to do it. Sometimes we have to do ugly things because we have no alternative. But if that happens, then you really have to be very, very careful and isolate that machine extremely well in such a way that it's definitely not at risk to be looked at by anything. And running it in a virtual machine can help you because you can set up extremely strong firewall features, for example, from the host OS, not from the guest, because the guest doesn't have that capability. Windows 3.14 had no firewall concept, but you can do it in the hypervisor level. You can implement a certain number of facilities, stopping the CPU to get crazy, and you can put numbers of control. But nevertheless, it's one of the very dangerous side effects of virtual machine from a security point of view. And finally, the hypervisor become a great hacker target. So if you can get in the hypervisor, so the
host operating system, you are the king. And so obviously, while it is difficult, it's extremely valuable. Once again, let's look at the reality of the risk, as well as I'm speaking today, in 2017, almost 2018, should I say. The risk is mostly for very critical infrastructure where they have a chance to be hacked by a team which are extremely professional, potentially with the backup of a state behind them, and they can afford that, or pretty valuable businesses where the heavy investment required to go against well-established technology, like what is used for running hypervisor in businesses, would require, it would require a very strong level of investment to actually crack this type of system. So it's not going to be for everyone, but just remember that it's still an opportunity, and so you have to apply your corrections and security patches on your host operating system and on your hypervisor code and application with extreme care, because if someone gets in that, you're really in big trouble. Now, let's switch from virtualization of the operating system to containers. We already talked a little bit about containers. Containers, we talked about it in the previous lesson when we talked about namespaces, and I gave two names. I gave the name of LXC, very light container, and Docker, which are very popular on the cloud. I also mentioned a virtual zone, which is really targeting at light virtualization. So container can be used in two ways. It can be taken as a light virtualization, which is definitely in general a bad idea. And I will come back to why this is a bad idea, but sometimes it's a bad idea is a good solution. So then you have to know what you do and be ready to deal with the side effect of such decision. The main interest of container compared to virtual machines is that they're extremely fast to be triggered and to start. They're actually so fast that they can be used for single use. For example, for those of you who use Google Mail, every time you start an action on Google Mail, I'm not saying when you log, I'm just saying when you start an action, you actually trigger a new virtual machine, which is dealing with your request. And as soon as that action is finished, that virtual machine is actually removed. It requires to write the code in a very specific way, but it can be very powerful. You can even have application where the database is only started when requested and killed immediately after serving the request. And that has the capability to scale extremely well. I have seen demonstration done by Google using their scheduler system called Copernicus, where they actually could create dynamically a load responding to web request on a web server when you had advertisement going on TV, where the numbers of requests were growing in 30 seconds from almost nothing to up to 2 million requests per second. And the system was capable to actually follow that with a ratio of success of serving the request without having a timeout, with a better accuracy than 99%. So very, very impressive capability when you do scaling. Not saying that it's easy, but it can do it. You can actually stack them directly on the operating system, but most of the times they actually are stacked on top of VM themselves, and that is a very common structure that we have in the cloud. Why do we do that? But mostly because I told you that VM presents the interest that we can do snapshot, and we actually can do replications, and we can do replication and snapshot. If you put them together, you can do transfer, which means that you can transfer virtual machines very easily from one server to another one. You actually have on some hypervisor, like for example VMware, you have the capability to do it hot, which means while the machine is working. So it's a very powerful system. So if you want to do a maintenance of a hardware, you have the capability to transfer the virtual machines on a new hardware or on a dated version of the guest OS, and guest hypervisor, sorry, host OS and host hypervisor, and you do the transfer dynamically without even having to stop the service. Obviously, that requires that everything behind follow, especially your network, which is where virtual network system becomes extremely handy, because if you move your web server dynamically from one town to another town, obviously all your IP address have to move at the same time, and you cannot move public IP address. So either you have a private network and you can move that dynamically, or you do dynamic update of your DNS, which takes time to replicate, so it would not really work. If you want to do that, you have to get virtual network capability. But it can be done, and it is actually done a lot. So as I've said, container is a type of light virtualization which is very, very fast to start, which means that we are going to be able to use them in a very dedicated way, and that's what I would advise you to do in general. Now, libvirt is a specific tool. It's actually a library, but it has a tool set on top of it which allows to maintain container and virtual machine with the same admin tool. That's a very interesting technology, so I advise you to look at it, because it allows to scale up. Obviously, if you just run container as single app container, that doesn't make much sense to use them with libvirt. But if you use your container as light virtualization, which is some case very valuable because it costs significantly less in CPU overhead, then it makes a lot of sense. For example, if you're using stuff like OpenZone to create pseudo virtual machines and you want to manage them like real virtual machine, it's a good solution. So you want to look at it. So let's look at the two big container technology widely available today, which are LXC and Dockers. LXC is a simpler one. And so you have your host, and on that host you are going to run multiple pseudo virtual machines. LXC, like OpenZone, is mostly used to create light virtual machines, where you will run a full set of servers, and you're going to maintain them like virtual machine, updating your code. So it can be done, for example, to create a delivery of code without having a strong overload on the host machines. So it will really behave as a fully functional OS with all the advantage of the disadvantage of it, which means that the data typically will be saved inside the container. Well, that looks something we all know. Traditionally, we save the data in the same machine that is running the OS. When you look at Docker, that is not the case. Not that it cannot be done, but definitely it shall not be done. It's a very bad idea to do it. So the way Docker works is that you start to have a base virtual machine image, which is as small as you can, on top of which you're going to add a set of virtual machines, and each virtual machine being actually a new service. So like it's shown in that graphic, you may have a base Ubuntu, and you're going to have a PHP and MySQL and management system, Nginx and WordPress and storage volume, which are going to be added on top of that. And the only one that is going to be writable is actually going to be the storage volume. Now, the way you're going to run each of your base container is by what is called layers. And so you're going to add your update on top of that. So, for example, your specific configuration files are going to be added on top on the base VM. And why this is done is mostly done that in order to allow to have the instance of the container, Docker container, to be really ephemeral, as very short life. You just get them to do a small job and you remove them. And so for the maintenance point of view, the model is that you actually replace it, because the data are never in the OS container. So the data are in a dedicated storage volume. The rest is just replaceable. It's a throw-away concept. I use my container, and if I have an update to do, I don't do an update. I make a new container which has a new code, and I just replace it, and my storage doesn't move. Now, that's easier to say than to do, and a lot of companies are using Docker like they are using virtual machine or like we are using LXC. And to be honest, this is pretty dangerous because Docker is definitely not designed for that. So if you are in an area which is using Docker from a cybersecurity point of view, you really want to know what's done, because unfortunately Docker is very easy, very easy to load ready-made container, and those ready-made container, most of the time you have no idea what is inside, and people pile up stuff. Yes, it works very quickly, but you don't know what you're piling up and which release of what you're piling up. And so the administrations from a cybersecurity can very quickly turn to an absolute nightmare. So that's what you really have to look at. So remember, it's very dynamic, which doesn't mean it's not dangerous. The good thing of dynamic, obviously, it can only be attacked when it's alive. So the time it's alive is shorter, so the exposure to danger is shorter, which is good. But the maintainability is more complex and requires significantly better organization and a very deep understanding of what people are doing, which often is not the case. So let's look a little bit at the Docker architecture. So we have the host, which is receiving the stuff, and there is a daemon, and that daemon is going to create a virtual network, and that virtual network is going to have the capability to connect containers. So how a container is done, first you're going to have what we call the image, and these images are taken from registry. Now this registry can be private, you can create your own image, but a lot of people are just taking them ready to go because there is a big set of registry, and this is a little bit the challenge because you have a known registry which are very well safe, known, and you know what you do, but a lot of people are downloading things without having any clue of what they are downloading and who has done it and what is actually inside. So this is a potential from a cybersecurity, the number one risk you want to put a stop on. If you're going to use Docker, you definitely want to have a very clear understanding of which registry are used and make sure that they're coming only from safe and trusted registry and nothing else can come in. Now once this is taken, it's going to create images. As I've said, images are piled together by layers. When you instantiate an image, you create a container, and that container status can be saved and so can be reactivated. The volume being almost equivalent to detachable hard drive. And the daemon allowed to be activating and making that cooking either by command line or by a remote API, which is a REST API, which then can be managed through web client or for traditional coding, which means that you can automate the Docker, and that's what is done in the cloud. So you can have stuff like OpenStack, which is using dynamically allocation of stuff to make it run. Now, as I've said, containers are done on namespace. There is one technology that is interesting to at least know that it does exist, called Clear Container. It's a technology dedicated to Intel hardware, where you can create a container which is running in actual hardware virtual machine. So it looks like a container, it's managed like a container, it's actually Docker compatible. But in reality, it's not using namespaces, but it's using hardware virtualization. Advantages and disadvantages. Obviously, isolation is significantly better because it's done by the hardware, and you don't run the same kernel, because in namespace, remember, we've seen that previous lesson, you're running the same kernel.
So here you have your own world. It still looks like a container, so you can maintain it and you can manipulate it like a Docker. You can also do the same in the Azure architecture from Microsoft. They also provide clear container. That's the pro, and the con is that it takes longer to start, because you have to start a full OS. And it takes a lot of more RAM and CPU resources, because in reality you're running a virtual machine. Now, it's not as heavy as a virtual machine, but it's not very far off. But if you need to implement a full hardware isolations in an architecture that was originally designed to work with a Docker system, it can be a useful hybrid model. It doesn't fit for everyone, but it's interesting to know that it does exist, because it can solve some problem where a technology has been chosen and then we realize that the risk is unbearable and we don't want to rewrite everything, especially if you have user remote APIs to do an automatic scheduling of your container and trigger automatically the startup and the teardown of your applications. It can be a very good hybrid solution. What about security? So container isolation is good. It's based on namespace, and the namespace provide a very reasonable isolation. It's not as good as hardware isolation, but to be honest, Linux is pretty trustable, and in general pretty good. The big challenge of container is that you don't know what is in the container. It's a bit like, in a harbor, you have a lot of container, you know how to manipulate them, they are easy to pack, they're easy to put on a boat, they go on a train, they go on a truck, but you don't know what is inside. And so the source and so the unreliable repository are far too commonly used. People were just looking for something, they make a quick Google, they find something, they download it, it works, they're happy. No clue what is inside. And that's not, from a cyber security, acceptable at all. The last point is that if you use your container like virtual machines, the maintenance can quickly get out of control. I told you that with virtual machine, you would have to scale up your maintenance and the automation of your maintenance and supervision of your IT system, likely by one-fold more than what the size of the company would let you expect. So, as I've said, if you have a company with 100 servers, if you put virtual machine, assume that you have 1,000 to maintain. With virtual machine, you could very quickly, get higher, but it's a bit slow. Now with container, you can assume twofold. It's so easy to use, it's so easy to deploy, it's so quickly done, it can be automated that before you will have time to realize what people have done, they will have just done it, and they will have started to trigger virtual machine every time there is a request coming, every time there is something, and blah blah blah, and it's too simple, and so it can get out of control very quickly. Now, if you use container as they are supposed to be used, especially Docker, by making stuff which are immutable, so you're never allowed to store any data on your container, and they are purely throwaway, and you have save repo, and every time there is a security update, you actually change your image set, and so next time it will be automatically update. Next time it will be used, that's what is to be understood. Then it can be very good, but you have to know what you do. So I would like to repeat security rule with container. Keep only safe repo. Check your repo and stop anything else. If you use container, use them for what they are designed, so one application per container. No more. No. If you are in the case where you needed to use container like virtual machine, then you have to assume the same rule than for virtual machines. Okay. But in that case, likely you don't want to use Docker, you want to use something like LXC or OpenZone that at least will not push your user to do things which can get out of control very quickly. Then it will look like a virtual machine. You can manage it through libvirt, and it becomes a virtual machine with a few limitations on hardware isolation.
but you maintain it exactly like that. But if you maintain it like a container, especially with Docker, one application per container should be the rule. So no full OS in a container, just a mini-merge packet set, no sharing of device, and all the traffic should go through network API. Why do I say that? There is a capability in containers, especially Docker containers, to actually call them privilege. And when they are privileged, they are allowed to access to the hardware devices. Then you don't really know what you do. You're in a very unknown world now. So as a production, I would not do that, and I would force all the traffic to go through network APIs. And then at least you have the firewall capability in the host machine and in the container that can be activated. Remember that in the container, everything is running as root. Now you can run it not as root, but as a dedicated user, but still it's single users. You only have one security context. The Docker container in particular today are not capable to implement mandatory access control. So everything ran under that simple context. So you really have no real control of what's happening in your container. But as long as you run only one thing, you just assume the global stuff is for that application. Container is immutable, so you should have no data in container and no update. I know for a lot of you, no update can sound a little bit strange, but you still update the container, but you don't update it by updating it inside the container, but you update the system by replacing a container by its update. So you just delete the image and you put a new image and you reconfigure your system to use that new image as a reference. So it's an update by replacement. Now, update by replacement are good, but it requires to test that it works, because yes, your volume of data is independent, but it's a little bit like having a /home on the system and having the rest of the file system on another hard drive, and someone, during your coffee break comes and replaces your main hard drive and say, oh, it didn't change anything because your home directory is untouched. Yeah, a few things may not restart that easily. You may have some side effects. So you must have continuous integrations to check that it really can go in productions. And you have the tool called the layers, which are definitely your friend to help you to do so. Now, troubleshooting containers can go very quickly, very complex. So you have to remember that containers are based on namespaces, which means that from the host OS, you see absolutely everything which is running in the container directly, which is not the case with a virtual machine. In a virtual machine, from the host OS, you have access to the resources indirectly, because you have enough privilege to request to potentially get access to it, but you don't have a direct visibility. You cannot make a PS command and see every single process is running on the virtual machine from the host, while on the container you can. You have direct access to that. You see what has been allocated, which software is running, which files are open, which sockets are open, because they are all open actually on the host kernel. So remember very well how to use your namespace. Go back to the previous lesson if you have a doubt, and really dig into that world. Everything is visible from the host OS. Same on network traffic. As I've said, you should really not use the sharing through devices, and everything should go through the network APIs, which means everything goes through the network, and the network is running on an internal bridge inside the host OS, which means that you can put all the monitoring tools and go to the previous lesson where we talk about the firewalling and capability to troubleshoot firewalling. All of that's available to you, firewall and redirection as well. Extremely short time life is definitely an issue, in the sense that if you have a container which has a time to live which is less than half of a second, it's going to be very difficult for you to go and look at what's going on. So you have a few tools with Docker. You can look at the last logs. Docker logs is your friend, but you can also redirect the log by configuration. The log actually puts you syslog, so you can actually redirect them, so you have capability to see that, and you can freeze the start of the container. That's another way to do it. but it's not obvious if it's a problem of a container crashing at the very beginning, or it can actually do things that you didn't want it to do, and it can be exporting data bit by bit and you don't really see it. So just be careful with that. But remember, it's only namespaces, and at that point you can actually check what's going on. Limitation of container are the same as namespaces. The host kernel weaknesses propagate to the entire system. It's not 100% host independent, which means that you may have some side effects that you didn't see on a container running on a host, for example, with an Ubuntu OS, and then in production you are on a Red Hat and it's different. Yes, it's not entirely independent. It's not like a virtual machines. So it means that your tests must be run as close as possible as your production. Its independence is pretty good, but it's not 100%. There is no real introspection. There is a tool for a little bit of introspections. You can look at the metadata which have created the container, but you don't really know what's inside. It's very difficult to know what it does. So you don't really have a complete control of what is inside, and especially you don't really know which libraries and utility are inside and may carry some potential weaknesses on the security side or CVEs, while you want them to be corrected. So the only thing you have is to trust your provider. So either you do your own container, you have tools for that, and then you have a team doing it, and they do actually the job for you, then you can trust them, or you have to work with a trusted source and you just apply the replacement strategy as fast as possible. So with all of that, you have to remember that it's very easy to create a mess, and a mess is a very unfriendly situation for someone who is in charge of cybersecurity. Frankenstein is never very, very far. You can, with container, create machines that no one really understands. Containers are just dynamically created, they are automatically scheduled, they are put on any locations, and everything is connected through a virtual network, which is created also dynamically. And at the end, you can have a system which potentially is working, but you don't control and you don't understand. And so if you are attacked, you can be in deep, deep trouble. And so the admin can get very quickly out of depth. As I've said, with container you can scale very, very easily to 1,000 times, 100 times, or 1,000 times bigger than what your normal operation should be. And obviously you cannot afford to support that. So it requires to have a very clear control of what you're doing. But still good tools, just have to know what you're doing. So as a summary, as I've said, namespaces as well as virtual machines provide a very powerful isolations for application and operating system. Mastering the side effect is not easy, and you have, through container and virtual machine, you have a capability to do things that you want. But remember that Frankenstein is not far away, and you could forget it very quickly. So I didn't create a homework for this time. This is a homework from last lesson. But you may want to play a little bit with Docker and look how it works. Very similar. A virtual machine you have already done, so you know that. You may want to have a look at libvirt and its capability. With this, I hope that this set of training on introduction to cybersecurity protection using Linux, or how to protect Linux subsystems the best as you can. It was of interest, and I wish you good work and good time in your professional life. Bye-bye.